Replacing TV.
Okay, let's get started. So we will resume with discussion on the quadrature hybrids and come on. अभी ये कहाँ से लेके आते हैं हमारे आप तो गया हाँ so all right, yeah. So this quadrature hybrid, we looked at the quadrature hybrid and the also called the 90-degree hybrid and the 180-degree hybrid quickly in terms of the functionality towards the end of the last lecture. We will go in a little bit more detail, but more from the perspective of the construction of this device using transmission lines, some practical consideration, and also some practical applications of where exactly does this kind of device get used in microwave circuits. Okay, so just to remind you, it's a 4-port device. The S matrix has this nice symmetric form. You can see from the structure also that there's very nice symmetry to it, essentially, which means that you can use any port as input and correspondingly the output ports and the isolated ports would be defined. The standard definition has the top left as the input port, then the two right side have the output ports, and the output, which is 3, has an extra 90 degrees with respect to 2. Okay, so that's the phase shift is in that direction. And then the 4th port is isolated, that in the most ideal case, no power sent in to port 1 will reach port 4. So in this sense, even though it's not exactly the same way, this 4th port is sort of similar to that extra resistor we had in the Wilkinson divider, which when you excite using the symmetric mode, which is the case for the standard Wilkinson divider, that when you put power into the input port, it creates an even mode excitation on the output. And that's why the resistor doesn't actually do anything. Okay, so it's similar to it. It's not exactly the same idea. Essentially, you have destructive interference at that port because of the various transmission line sections and the path lengths. So you don't get any power coupled. You again see lambda by 4 sections, in fact, in all the 4 arms of the square in the middle, and which means that it only works ideally at 1 frequency, and then the performance will degrade as you go away from that frequency. So again, you can use some figure of merit to define the operation band. And then there are methods to increase the bandwidth by making this multi-section. So I'll show you some examples of commercial products which show some possible design variations which allows you to get a larger bandwidth. And finally, I will discuss the one application of this in microwave circuits. We will do the same thing for the 180-degree hybrid as well. There in particular, I'll take an example of an experiment which I carried out during my thesis almost 20 years ago. So this experiment was probably 15 years ago. And where the properties of the 180-degree hybrid were critical to achieve the operation we wanted to do. Okay. So yeah, so you get equal power split and you have 90-degree phase shift and you have an isolated port on that. As I mentioned, the even odd analysis given in POSAR, you can go through it and see if you can follow that. But we're not going to look at that, and I'm not going to ask those kind of analysis in homework or in the exams. So in the last part of this section, it talks about a few of these things, that the quarter wavelength, which I already mentioned, limits the bandwidth, but you can use multi-section things to increase the bandwidth. You can also modify this design to get unequal power division. So right now it's equal power division, so you can do that. And you can also get different impedances at the output ports if your application requires it. Usually any connectorized object will always be 50 ohms at all ports, because we don't really have that many different port impedances for the actual connectors. There are really only two standards, a 50 ohm and a 75 ohm standard. And the 75 ohm is mostly used in cable TV, and it's again rare these days. Okay. So one other point it mentions here is, and I think I had briefly mentioned this in the last lecture, is the discontinuity effects at the junction. So what it says is that practical point to be aware is that discontinuity effects at the junctions of the branch line coupler. So the junctions are where these different transmission lines meet, may require that the shunt arms be lengthened by 10 to 20 degrees. Okay, what do they mean by that? We go back to this, this basic circuit here. The problem here is in defining which boundary do I choose to specify the length of a section of transmission line here, right? So, for example, if I choose this one, this is easy because there is some reference here and there's a clear reference where it ends at this point of time. But if I look at this one and this one, then I don't really know where this one ends and where this one starts, or where this one ends and where that one starts. So there's a little region of ambiguity where these kind of things intersect because they have finite widths, right? In microwave office, when I'm going to use ideal transmission lines, I'm going to be having this type of, I mean, the shape is coaxial, but it has no meaning. But I have these wires at the end. Okay, those are not, there's no such wire in the real space. So when I connect two transmission lines like this has no meaning. It's just zero length contact. So I can define these numbers very precisely, but when I actually translate that into a real design, so this could be a microstrip design or a strip line design, then one has to worry about this. And you also see these kind of things they have done at the edges, like give it a slightly smooth, because this middle part is supposed to have a smaller characteristic impedance, so it's going to be wider. So they have used this little taper here on one side to make it a little smooth. So what they are saying is that this length here might have to be longer than what you calculate for the ideal lambda by 4, so by 10-20 degrees. And that is something you have to do by trial and error through a finite element simulation. Okay. So these are things one would have to optimize, and it's almost, very complicated if you want to analyze this analytically and say, okay, I need, you can probably guess that you're going to need an extra length, because you could say, well, this part is all that transmission line. So maybe this one needs to go to the center point of this. Maybe there's some extra length is needed there. Okay. So in microwave office, there are actually some structures. I don't remember now. Of course, you can draw the full EM structure like we did for some of the transmission lines. But in those pre-solved models, remember the one which had the substrate and the trace lines things separately, which are somewhere in between a full EM simulation and a basic circuit analysis. They're like pre-solved models of certain structures. They might have a structure which is basically like a junction of 3 transmission lines. And then you can use that to run a faster simulation and figure out these kind of deviations quickly. What should be the actual design look like for it to work properly like a 90-degree hybrid. Okay. So let's move to the, one second. You need transmission lines. Again, remember the active part of this is really just the 4 arms of the hybrid. $50 divided by 1.414 is 35.36. Going to choose again 6 gigahertz as my center frequency. Let's put the ports using the same convention. So 1 is here, and then 2 is here. Here. So let's do linear magnitude. So into 2 from 1 to 3. Okay. So pink and blue are S21 and S31. S41 is the isolated port, and S11 is just the matching part. So exactly at 6 gigahertz, S11 is 0, S41 is 0. So one is for matched to 50 ohms, and the other one is perfect isolation, no transmission to port 4. And then you have exactly 0.7 in amplitude, because this is the S parameters magnitude. So square of that would be half, just 3 dB power. Okay. So one interesting thing to note is that even though there is this very nice symmetry, port 3 and port 4 are not identical as the frequency changes. right? They have the same transmission exactly at the design frequency, but the rolling off of this is not the same for port 2 and port 3. And that's basically because the path length from 1 to 2 and 1 to 3 is actually different. So there's more number of transmission lines involved. Let's see if the intuition actually works through. So 2 here is actually rolling off faster, which is kind of, I guess, counterintuitive, but it's probably a slightly different reason because of interference, because there are these paths as well. Right, I've got the numbers, right? 2 is the straight one, and that's the blue one. Yeah, so the blue rolls off faster. The matching and the isolation, they kind of go together, but I don't think there is any fundamental connection there, but then they start to deviate out over there. Okay, so I'm not plotting the other quantities because it's completely symmetric. It will be fine. The one thing we will look at is how to check the phase. Right? So let me duplicate this. Oh no, okay. And I'm going to delete the 4 1. The 3 1. And I'll plot the angle. Okay. So this discontinuity is not real. It's because this phase here is going to minus 180, and then it wraps around to plus 180. We can actually fix this by using this angle U command here, which basically unwraps the doesn't allow it to wrap between plus minus 180 degrees. So at 6 gigahertz, the phase on 3 with respect to 1, okay, remember it's S31. So this is the phase with respect to 1. It experiences a minus 180 degree phase shift. And this one here experiences a minus 90 phase shift. So that's why the difference between the two is 90 degrees. So remember the phase convention here. When we saw that what a length of transmission line, how it accumulates phase, you always see this phase going from positive to negative, right? So that is what an increment in phase is. So if this is minus 90 and this is minus 180, it has a higher phase shift compared to that point. So I was just saying this because if you just subtract the two, it looks like the phase is going in the opposite direction, but that's just the convention of the phase. Okay. And you see that these two lines they're not exactly parallel, but they're reasonably parallel, at least say between 5 and 7 gigahertz. So the phase shift, the phase difference between the two arms is being maintained close to 90 degrees over a range, because that is, again, one of the important things which is a specification for a 90 degree hybrid. And it's usually determined by a number called phase imbalance, where they tell you how much is the phase in addition to the expected 90 degree, plus few degrees, minus few degrees. And they will give you some worst case scenario. Usually it's quoted. So I'll show you a data sheet in just a little bit. Okay. So you see that the amplitude imbalance here is also not that great beyond like maybe a few hundred megahertz in the middle. And then it starts to deviate. And in fact, it deviates quite significantly, even though this one sort of remains at roughly half for quite a bit. This one starts to drop significantly. Okay. So that's what the simplest 180 degree hybrid constructed in this method gives you. So let me now show you. So this is a commercial 90 degree hybrid coupler. you can see the ports in -3 dB 0 and -3 dB 90 degrees shown here. And you can sort of see the symmetry. It's very similar to how we draw it. So this is 1, that's 2, and that's 3. And 3 has 90 degrees more phase shift than 2. And then the isolated port is over here. But notice the bandwidth here. So look at the frequency range. It says 1.4 to 32 gigahertz. Okay. So it's a huge range. And that's why this thing is also bigger. It's sort of long in this direction, because there's a lot more transmission lines being packed here. Coupling 3 dB, that's the fact that it's an equal 3 dB splitter. Amplitude imbalance plus minus 1.55 dB. Okay, what this means is that over the entire range of frequency from 1.4 to 32, imbalance will not be more than plus or minus 1.5 dB on top of the 3 dB, right? Or if you take the difference, that difference will never be more than plus or minus 1.55 dB. Similarly, the phase imbalance, it will be within plus minus 12 degrees. So that's how they will specify this. Of course, you have to see at all frequencies, you can measure it. Usually they give you this curve as well. For some reason, they have not provided in this case. Between the two outputs. So let me just expand on this again. We would like the two amplitudes to be equal and half of the input power, right? They don't guarantee that they will be half of the input power. That's a separate quantity. What they're saying is that whether the difference between the power is going to be always 0 dB or not. And what they're saying, it will be somewhere between plus or minus 1.55 dB over the entire frequency range. Right? If we do it for the system we just looked at, if I now turn this into dB, so already if I go at say 5 gigahertz, oh, I thought I was sharing the screen. What? Oh, this thing has gone to. It's gone into extended desktop mode. Oh. I'm getting very confused now. What am I doing? I have to share the screen so that it's available on Zoom, but I don't have to share the screen. It just has to be on the projector for you guys, right? All right. Now you can see. Okay, good. So here, at this point, at 5 gigahertz, this is about minus 4.5 dB. And that one is about minus 3.2. So this is already 1.3 dB deviation at 1 gigahertz away. And they are guaranteeing 1.55 dB over the entire band. So that's what it is. Similarly, if I look at this plot, I can find out at what range the phase changes. Okay. So that's what that number means. So then they also say isolation is greater than 12 dB. So which means the worst isolation you will get is at least 12 dB. So that's like a factor of 10 and then a little more in power. VSVR, I think I'd introduced this term long time ago. This is another way of measuring reflection. This is called the voltage standing wave ratio. And a voltage standing wave ratio of close to 1 means perfect, no standing waves. And instead of the rule of thumb of minus 20 dB return loss, it's basically giving the matching of all the ports. So this is the part I was saying, that they don't guarantee it will be 3 dB because the structure inside will have its own losses. So what is typically called insertion loss. So it says less than 3.5 dB. What does this mean? It means that the output at any port will be at least greater than, or the maximum attenuation you will get will be less than 6.5. 3.5 here plus the 3 dB you have. So this is the additional loss you will get between the input port and one of the output ports. So they're saying it will be, that is the worst case scenario. These are sort of irrelevant. They are related to how much microwave power you can send through the systems. Most of these things are often designed for very high power applications. So you can put like 20 watts of power. And if you are doing pulsed power, you can go up to 3 kilowatts. So these are all like orders of magnitude. The typical powers one uses in routine circuits is milliwatt, maybe even less. Okay. Then, of course, the connectors is just SMA, weight, and operating temperature. Okay. So something this PowerPoint, I think, creates a problem. Yeah, I think when I do PowerPoint, it goes into, gets rid of the screen mirror thing. Okay, so this is actually, it's like a product note from the same company, Krytar, which makes this. This is an old one. They said they have introduced 90-degree hybrids covering 1 to 18 gigahertz. Here is some specs for the 3 different models they have. Again, coupling, amplitude imbalance. And now it's 0.4 dB plus minus. It's quite good. Phase imbalance somewhere between 7 and 10 degree. Isolation greater than 17 or 20 dB. Insertion loss less than 1.5 and maximum standing wave ratio of 1.3 or so. And here's actually the data from the sheet. So the left one is going from 1 to 12.4 gigahertz. You can see. So that's the amplitude imbalance they have plotted. Basically, they have taken the difference of the 2 outputs, and ideally it should be 0. So you now get 0, and at the most you get, this is like the worst point, minus 2 point something. But it can be go both up and down depending on which of the thing is. But that's not always the case. For example, in this, the power on one of them is always less than the other one. You don't see any going up and down. That's because it's basically a single stage system. Okay, and similarly for phase imbalance, you see it's very close to 0 at low frequencies, and then it sort of gets worse and then stays over there. What does this circuit actually look like? So they, of course, won't give you all the exact details because it's probably a patented thing. But here you see a sense of how it is made. First of all, it's made in strip line, which means there is dielectric both top and bottom. And this dashed line actually means that the 2 transmission lines are on opposite ends of a piece of dielectric. So you have 2-sided things. So the coupling is happening through a piece of dielectric. Just what's going on here. So it's a multi-layer board. So it's not a standard microstrip or strip line. It's called a strip line because there is always dielectric on both sides of the transmission line. but the transmission lines themselves are existing on opposite sides of a very thin dielectric. So I'm not 100% sure, but I can roughly sketch what it might look like. So there is this extra layer of dielectric which is in the middle. This is the standard dielectric. And then here you have your metal things. So if in between these two dielectrics there was just one metallic plane, that would be the standard strip line. What's happening here is that this is actually another very thin dielectric, and there is one transmission line sort of going on top, another one going on the bottom. So if you ignore the fact that this is a very thin, if you assume that this is 0%, basically these are just two strip lines with these as the ground planes and those are the dielectric. This is created in order to have this kind of a crossover geometry they want. So they are taking like two transmission lines which are crossing over, and it's the proximity between these two lines which is giving rise to this interaction and coupling. So this is a completely different design. This has nothing to do with the simple structure we just looked at, this type of one. This is a completely different design, which they have. I mean, this is their invention and probably patented.
Why does it need to be very close?
Because you want those two transmission lines to be close to each other to get coupling. If they were far away, if this was thick, then these two transmission lines will be far away from each other. Essentially, it's a trick to have them cross over without having to make a crossover. Right? It's just you just like made it on two sides very close to each other. They want you to, those fields have to interact with each other. And you can get a sense for how expensive these things are. Typically about $500 to $1,000 each. And this is the price from some years back. They're probably a lot more now. So they've actually also given a reference for the basic idea of coupled transmission lines as symmetrical directional couplers from 1955. So anyway, microwave engineering is quite old. A lot of the work happened during World War with radar-related developments, as with many things in the past. Okay, so that was that. And then I wanted to show you one example of what's the purpose of one of the standard places where hybrid gets used. There's going to be some new information here because we haven't studied some of the other components. But this guy here, let's see if I can annotate here. This guy here is called a mixer, okay, which is basically a multiplier. Okay. It takes L, multiplies it by R, and gives the multiplied thing at I. I won't discuss now how it does that. We will probably cover this towards the end of the course. Usually, L and R at a higher frequency, higher and similar frequencies, and this is at a lower frequency. And what happens is that if you now send in two, and this is all accepting microwave signals in some range. If you send in two signals like say sine omega 1t and then sine omega 2t. So these are the two signals going at L and R. It's going to multiply. So what happens when you multiply two sines? You get sums and difference term, right? Standard trigonometry. So the sum term will be at a much higher frequency and the difference term will be at a much lower frequency. And if these are similar in frequency, that low frequency will actually be quite low. Okay. So usually because of the nature of the construction, the higher frequency actually gets filtered out. And what you get at the IF is a term which is in this frequency range. So that's the purpose of a mixer, to create these difference and sum frequencies by multiplying the two together. So you can, this is a very common thing which is used for moving signals between frequencies. So for example, when you have amplitude modulated signals, say in AM radio, that is a small frequency multiplied by a large frequency and then transmitted. So if you want to bring back the smaller frequency again, you multiply it with the high frequency term, and then you get the difference frequency, and that contains the information which is actually encoded in the signals, right? So these are very, very crucial things. You probably saw some of these when I showed the diagram for the network analyzer, because there's also this frequency conversion, because often the information in a high frequency signal is not contained in the high frequency oscillation part, but the slow variation of the amplitude and the phases, right? This is very typical of how information is transmitted using a high frequency carrier wave. So you always have to recover that. So you have to do some frequency down conversion. And this kind of thing allows you to do that. The process also works in reverse, where if you send in signal on L and I, it also gives you L into I on the output R. Okay. It's kind of symmetric in that sense. Okay. The only thing which is not interchangeable is that the L part is often, L stands for LO or local oscillator. The power needed there is much higher for biasing the system in the right nonlinear range, but let me not get into the details. So in this mode, you have a high frequency multiplied by a low frequency signal, and then you get something in the high frequency range. But now you can get high plus low and high minus low as well. Here, that filtering effect doesn't happen naturally because this high plus low and high minus low are close to each other, because this low frequency is, I should probably write it at low, because LO is also LO. It's L. So it's very confusing. So I just mean to say high frequency and low frequency. Okay. So that's the job of this mixer. Okay, it's sort of a long-winded story here because I have to come to that. There is a technique for creating. So the second one is the one I'm going to focus on. So if this I is actually a function of time, okay, and I multiply this with L. So imagine that so LO is now some sine omega t, where omega is a high frequency. So in fact, let me put this here, omega LO here. So this I of t is like an envelope, right? It's an amplitude modulation. So this is, for example, will be useful to create a pulse like this. So the fast oscillating part in the middle is the high frequency term, and you want to turn the pulse on and turn it off with some shape. So if you program that shape into I of t, then you can do this. The most generic way of doing this is that you would like both the amplitude and the phase of that high frequency signal to be controlled. And that you cannot do just with having this I control. Okay. What you need is something like this: I of t sine omega LO of t plus Q of t cosine omega LO of t. Okay. This is again just trigonometric identity. If I of t and Q of t were themselves sine and cos, then you get some sine and cos, and that will give you sums and differences, right? But if this I of t and Q of t are pulses like this, then you can actually, by controlling I and Q, you can get a most generic A of t sine omega naught t plus phi of t. Okay. So from this, if you expand the sign, you see that AT phi t, AT into cosine of phi t is what I is, and AT into sine of phi t is what Q is, right? So this is just to do the mapping. Now, how do I create this kind of a signal using this method? So in fact, the diagram is drawn there. I'm going to erase the top part here.
Final frequencies in sine omega naught or omega LO.
There is no omega naught. Everything is LO, just bad writing. All the frequency right now, I've written it as omega LO because that high frequency term only goes into the LO port of the mixer. Okay. So if you now look at this diagram carefully, here is the LO. So this is sort of like your source sine omega LO t. This is a 90-degree hybrid, which is the thing we are studying. So there, what you're going to get is that if I ignore the overall phase shift, which you get anyway, because one is minus 90 and one is minus 180, then if one of them is sine, the other one is going to be cos, because it's 90-degree difference. So then what you do is you take two such mixes and then send the sine and the cosine component from the original sine component to two different mixers to their LOs. And then the I port of each of those mixers becomes I and Q. Okay, so this I and Q, the nomenclature is I is called in phase and Q is called quadrature phase. Quadrature meaning 90 degrees. Okay, and then the output, because one is going to be IT into sine omega t, the other thing is going to be QT into cos omega t, then you need to add them again. So this here is just a regular splitter operating in reverse. It could be a some other 4-port system as well with the 4th port hidden here, and then you recover. So at RF here, you get this guy. This is one very standard location in microwave components where this kind of stuff is used. In reality, all of these components, the 90-degree hybrid, the two mixers, and the final combiner, all of this could be on a single chip as a single, and if it is that, then it's called an IQ mixer, which is a 4-port device because LO, RF, I, and Q, whereas a regular mixer is only a 3-port device, which is just LO, RF, and I. So these 90-degree hybrids are extensively used in this kind of stuff to create 90-degree phase shifted signals. Okay. Now there are variations to this. If I go to again, I have to. Oh, jeez. What is that? So this bottom one was the one I just showed you. So you have the LO going through a 90-degree hybrid to two mixers, I and Q combined, and then combined by a regular hybrid. You can have a situation where the combination is also done through a 90-degree hybrid. This will create interference between the two output terms and allows you to do something called an image reject mixer. So this will have two 90-degree hybrids in the same circuit and a regular hybrid. And there are many other variations where you can, that one is now the reverse of this. Now the input is coming from I, And instead of creating I of t and Q of t separately, if you actually want I of t and Q of t to be just 90-degree phase shifted, then you can use a low frequency 90-degree hybrid to create the I and Q 90 degrees phase shifted. The LOs are 90-degree phase shifted using the standard mixer here, and then the RF are combined. So all of these allow you to play around with these different combinations, but the 90-degree hybrid is an essential component of all of these things. This is one very common place where you will see this being used. And last time I told you that it's also the equivalent of the beam splitter in optics. So there are microwave quantum optics types of experiments which people do where these hybrids are quite essential. And they basically play the analogous role as in the optical system. Okay, right. There. Yeah. So we now move on to the 180, but are there any questions about the 90-degree?
About these IQ mixers, how can we know what is going on inside the part that you will be covering that how do they work?
I will discuss how a mixer works. The regular 3-port mixer. So there'll be maybe 2 lectures on nonlinear components. Right. So 180-degree hybrid, again, we had looked at it briefly. Just to remind you, it has 2 input ports, one which is called the sigma port, other one is called the delta port. If you put a signal on the sigma port, you get equal power division and equal phase shift on the output. And no power to the delta port, so that's the isolated port. So in that sense, it's identical to the 90-degree hybrid. But if you put power into the delta port, then you get signals on 2 and 3, but with 180-degree phase shift, and again, no power going to 1. And it's symmetric. You can interchange the input and the outputs, and it wouldn't matter. This one, the 4th port, the delta port, is closer to the extra resistor in the Wilkinson divider. So here you can really think about it in that sense, because the voltage drop there only happens if the excitation is differential. And that is true when you look at it, the operation in the opposite direction is that if I send in 2 signals which are in phase to port 2 and 3, they will come out of port 1. So this also, the reason, in fact, it's called sigma and delta, it's kind of strange that I've talked about the operation from left to right. It's called sigma and delta because this is equal to 2 plus 3, the sum, and this is equal to 2 minus 3. So if I send in some general signal on ports 2 and 3, no phase relationship, the sum of that will appear on sigma, and the difference of that will appear on delta. If these are phase coherent, then you will get interference. If they're exactly equal and same phase, then you will get no signal on delta. Everything will come on sigma. If they are equal and opposite in phase, they will all come out on delta and nothing on sigma. So in fact, this is now connected to your even odd mode idea as well. If I send in an even mode excitation on port 2 and 3, then I will get all the signal at port 1 at the output. And if I do an odd mode excitation, I'll get all the signal on port 4. Okay, and then again, you can, because of the symmetry, it all works. Doesn't matter which one is input and which one is output. Okay. Which means if I only send signal from 2, I'm going to get equal division here. And that's actually obvious from this relationship, right? If I send signal on 2 and 3 is 0, then on sigma, I'll get 2, and on delta, I'll get 2. And of course, there's a factor of 2 there because of the power conservation. But if I send a signal on 3 and 2 is 0, then port 1 will have 3 and port 4 will have -3. So the minus there means 180-degree phase shift. Okay. So that's how the functioning of the 180-degree hybrid is. And I also briefly showed you this structure here. There are multiple ways of making it, but this rat race hybrid, which is just a circular transmission line with characteristic impedance √2 Z0 and a total length of 6 lambda by 4 with these positions between the different ports coming in, gives rise to this function. Again, there is a design frequency, which is set by what lambda you have chosen here. And that's where you'll get the ideal operation. And everywhere else, the performance will degrade. But we will see one thing which actually can improve performance in just a little bit. I also motivated that why sending a signal at 1 gives you an equal phase shift between 2 and 3 is because they are equidistant from that particular port. But from port 4, they are not equidistant. Okay. And the rest of the stuff is the same. And is there something here? Okay. This is just again a computed frequency response, but we will just see that in microwave office. So let me now move to back to the microwave office here. So I'm going to need 4 sections. Lambda by 4, 6 gigahertz, and 70.7. See if I got this right. So this is going to be 135. Port 1 is here. Port 2 is here. So again, I'm trying to use the same convention. So you see that port 1 is equidistant from 2 and 3 with a lambda by 4 section on either side. And then, yeah. Sorry? Oh, sorry. Yeah, you're right. I was actually wondering, it looked wrong. I was somehow thinking lambda by 8 in my head. This will be 270. Okay. 1, 2, 3, 4, and this is all 50 ohms again. So I don't need to draw the 50 ohm sections on the output. Let me duplicate this graph. Okay, I have to change the transmission. So the port 1 is the sigma port and port 4 is the delta port. So we will look at transmission from 1 to 2 to 3 to 4 and 1. Oh, sorry, one of them, even this is not in dB. There you go. Okay, so again, 2 and 3 equal split with an amplitude of 0.7. So 1 over root 2. Square of that is 1/2. And then they deviate as expected. 1, 1 is matching, it's 0, and 4 is isolation. Okay. So this is for the excitation from port 1 and looking at the output in all the other ports. If I do do the same thing, but now from port 4, so it's going to be S24, S34. This is now exciting on the delta port and looking at all the outputs. So S44 is just matching, and S14 is the isolation. So you see that basically exactly the same. Right? So again, you have equal power split and matching and perfect isolation over here. So of course, we need to check the phase. So let's go back to this previous one here. Let me duplicate that. And let's go to schematic 2. And I will first look from port 1. Okay. So port 1 means the twos are in phase. So you get 0 degrees, no change between the two here, and then they're sort of close to each other. And it is this weird kind of behavior, but the phases are close to each other. So they are in phase. And if I now change this from port 4, sorry, I changed the wrong one. So you have plus 90 and minus 90 to give you a total of 180-degree phase shift between the two signals. Okay, so again, they're sort of parallel, but not exactly. So you'll have some amplitude and phase imbalance here as well. Yeah. Okay, so this part is straightforward as expected. Now we will discuss why this kind of a hybrid can be useful. Okay. I'll just keep it like this so that it's big enough, right? Focus first only. So this is your hybrid. Okay. And only focus on this part. Many of you have probably done some low frequency experiments measuring DC IV curves. One standard way of doing that is to use these twisted pair wires, right? Do you know why one uses twisted pair for low frequency signals? Volume.
Magnetic flux and
What happens to the magnetic flux?
when and when wires are separated, then there will be magnetic flux related to that wires. But when I just
Okay, but it's the other direction. What you are trying to avoid is varying electromagnetic fields or magnetic fields which are present in the location of the wire from inducing a current or a voltage across those two wires. So if you tightly bound two of them, then basically you cannot induce any differential currents into the circuit. So this is to avoid pickup, because if you have, let's say, a very sensitive device, say for example a Josephson junction, which is represented by a cross, and you have some circuit, there's some resistor, and then there is some voltage source here, this entire thing can form a gigantic loop through which you can thread a magnetic field or electromagnetic radiation of low frequency. And if that varies, it can induce currents and voltages, and that could be detrimental to your experiment. So this pickup, as you typically will say. So the way to do it usually is that you take this and you close this loop, and then you have a very like a tightly wound twisted pair wire, and then you connect it to your voltage source. Okay, so this is very standard. Also, having two conductors means that you can actually keep it separate from the ground. So this is often you have isolated sources. So ground is also completely separated. So you can have plus minus. So you need special sources and detectors for that. So for example, a battery is an example of a differential source. It doesn't have any ground reference. You can give it. There could be an overall ground of the experiment, but you could just have plus and minus. So similarly, there are amplifiers which can be isolated from the ground. And that is again to avoid noise, which could be there on the ground line. And avoiding ground loops. So the challenge in this experiment was that I was trying to combine a low frequency DC measurement and a high frequency RF measurement. Now, hold on, not disturb. Now, what is the one very standard things we have seen in all RF signals is that one terminal is always ground, right? In your microstrip, you have center conductor on the top. There is a ground plane. In CPW, there's two ground planes on either side. Only maybe in coupled strip line kind of things, there is a possibility of having two conductors and a ground as well, which is separate. So even in these low frequency measurements, you have twisted pairs and there is a ground reference. The point is that the two twisted pair lines will always have plus and minus V with respect to some ground. So they will have 2V across them, but there is a ground reference. So how do you make the two compatible? And that's where the hybrid comes in. And it's sort of like using two lines. So what you see here, if you look carefully, there is a DC signal chain which is coming all the way here. And that is coming via twisted pair. And those two wires are going here. Okay. These are the two wires I have put across my device, which is inside this blue box here, which is basically a Josephson junction shunted with a capacitor. Okay. But it conducts at DC. So that's my DC part of the circuit. There is this device which is written here called bias T. Its purpose is to just combine high frequency signals and low frequency signals with respect to ground. Okay. So this is like plus, there's plus U here and minus U here. And in order to maintain that symmetry, what we have done is we have taken the RF signal here, put it to the delta port, and created a plus and a minus version of the same signal. So there are two anti-phase signals. They then come through a ground reference coaxial cable and then gets combined with the DC. So what you have done is you have taken a plus V RF signal, combine it with a plus V DC signal, and a minus V RF signal, combine it with a minus RF DC thing. Okay. So this kind of stuff is called a differential mode of excitation. Because you have both plus and minus, it's not plus with respect to ground. So this is a 3-conductor experiment in that sense. There is an overall ground reference, but to create this differential RF signal, even though your signal is actually coming from only one, there's only one source, the hybrid creates that equal and opposite division you want. Of course, it's not perfect. There is going to be some imbalance, but your device at the end is actually also a 2-terminal device, right? It doesn't have a third explicit terminal. So it maintains that whatever imbalance it is there, and then you can go. So this allows me a way to maintain twisted pair DC measurements without connecting. See, there was one other way I could have done is that I could have grounded one of the terminals right at the end. But then I don't maintain the full 4-wire or twisted pair measurement. It then sort of effectively becomes a 3-wire measurement because you have a ground imposed now. So that is not ideal from the noise perspective. But here in this experiment, it was crucial that I was able to do both the DC and the RF experiment on the same setup without changing anything, with all the noise protection you could get with the best practices. Okay. So 180-degree hybrids in this context are very, very important for doing this differential excitation type of experiments. In this very specific case, you have used to combine DC and RF, so that differential DC and differential RF can work together. Okay. Otherwise, we'll have to ground one of the terminals. And that was crucial because we were very, very worried about noise coming in from any of these things, because the experiment was actually trying to measure quantum noise. And we wanted to show that this quantum noise was matching with the prediction of quantum mechanics. So any extra noise from any other source would have been a disaster for this. So this is a very nice example. I mean, one of my proud moments in my thesis to have figured out this circuit. It's not some great invention or anything, but for me to have figured out at that time, it worked really, really well. Okay. But how can one do, so this is like an explicit example where this hybrid was actually like a commercial device with multiple connectors. Sorry, that's just me. It's 15 minutes to go. I'll wrap up in 10. So it's a commercial hybrid, just like the one I showed you in here. It has a very similar, in fact, it was from the same company. It looks like this. Let me see if I can pull up. Yeah. So here is an example of 180-degree hybrid. This one goes from 1 to 26.5 gigahertz. Again, these are similar to the 90-degree hybrid, different kind of design, sigma, delta, and 2 and 3. So this is essentially what is here in this location. Okay. But there are other ways of using this, and this was another circuit which we designed. And this was actually during my postdoctoral days, even though an early version we had made during my PhD days. And there are some interesting things going on. So we will just finish this discussion. This is again because I'm trying to excite a device which has 2 terminals, and one of them is not ground. Okay, there's no simple way of connecting it to ground because ground was underneath the chip. Okay. Towards the end, I'll tell you how to actually do it in a much simpler way, which is how we do it now. So we again wanted to create a differential AC excitation to excite the system with plus minus kind of voltages. So that's exactly what this is. This is a 180-degree hybrid with a few modifications. Okay. So first thing you notice is that there is only 3 ports, right? There is 1 port here, and there are these 2 coming out of the ring. There's something funky going on here. I'll comment on that just a second. But there is no 4th port. Okay. The reason is, if I'm only interested in doing a differential excitation, so I excite from delta. So this here is delta port. This is 1 and 2. Oh, sorry, 2 and 3, I guess. And then 1 would have been here, right? Right in the middle of 2 and 3. But in this mode of operation, 1 is supposed to be isolated, right? Ideally speaking. And because my device at the end is also differential, it cannot convert the odd mode excitation into an even mode excitation unless there is an imbalance in it. So in the most ideal case, these two signals are coming out of the hybrid in opposite phase. They go and excite the system, and then they reflect back with the same 180-degree phase shift between them. It's very critical that in order for that to happen is that everything is symmetric, like this path here and that path here have to be exactly identical. I'll elaborate on that in just a second. It's not okay, I guess I forgot to emphasize this. At the end of this device, so this is delta port, this is 2 and 3. What I have is this. It's an inductor and a capacitor. It's an oscillator. There is no power absorption going on here. Okay. So it's going to completely reflect back. If you remember back at the beginning of the lectures, we talked about reflection measurements on an LC oscillator. This is the same, but the differential version of that. Okay. There are some subtlety to it. We'll see if we can get to that today, or we'll continue in the next lecture. So these two things go opposite phase, and then they might themselves undergo some phase shift, but whatever phase shift will happen will be symmetrically happening on both of them, so that ultimately they remain 180-degree phase shifted. And hence, in the reverse direction, the whole thing works exactly the same way. Two anti-phase signals on ports 2 and 3 will constructively interfere on the delta port and destructively interfere on the sigma port. So I basically don't have to worry about the sigma port. So we just removed it, right? Ideally speaking, I could have put a little 50 ohm line here, just like shown here, and then terminated it with a 50 ohm resistor. Okay. That would only ensure that if there was some imbalance, that power will actually go and dissipate in that 50 ohm, which is actually sort of bad for this circuit. We don't want the power to be dissipated anywhere. So we just decided to get rid of it, and it turned out that it works fine. So this is a way of converting a single-ended excitation. What do I mean by single-ended excitation? That at this point, it's some plus V with respect to ground. And then here, it's some, plus V prime over some plus V prime and minus V prime. Okay. The part here in the middle is a trick. And again, it was strange because we were playing around again with microwave office, and we discovered this effect. Okay. I was staring at POSAR today, and in fact, I will show you in a little bit that in one of the pictures there, I see this kind of a section, though it doesn't say what it does. So this obviously must be again a well-known trick which we haven't found in the literature. But we found that doing this, so what's actually happening here in terms of the which one works?
I mean, like you're basically increasing the width, you're
decreasing the impedance, right? So all I have done is that lambda by 4 section between ports 2 and 3 has a much lower impedance. In fact, what we found out that 25 ohms, I think it was 25 ohms works best. And we saw that it improved the amplitude and phase imbalance between the two arms. It made the frequency dependence a little bit flatter, which is what we would, that's better for the performance here. Okay. So this is another way of creating a differential signal. And this is now actually a 3-port device. The 4th port doesn't exist. What would happen if you imagine that there was a 4th port here is that any imbalance in the signal will come here. But then what's going to happen? It's going to see an open termination. So it will reflect again, right? So you have to be careful because those kind of reflections, so there is going to be a reflection point here. And that reflection, if it gets reflected and goes back, it's going to create an even mode excitation on these two. and then it'll reflect back again, and you could set up some kind of a resonance over there. So it's very important that the paths are as identical as possible. Now, let me elaborate on that. Phase here could just be changed with time or length, right? So imagine I have two anti-phase signals propagating along these two lines, the ones which are coming out of the hybrid. And right now I had a perfectly symmetric situation, so I said they came back like this. Imagine I increase the length of one line by exactly lambda by 2. At the end of that, what's going to happen? This is going to become in phase. Now, okay, these are at two different points, but I can always make one line come back and wrap around itself, right? So it's in phase, and then it has to come back again, and then it could be out of phase. But if it was lambda by 4, then a total round trip over there will give rise to 180-degree phase shift, and it will return in phase. Then it will not show up at this port as you would like. So by changing the length of the output, you're essentially creating this imbalance between this even and odd mode kind of situation, right? So in these circuits, that's maintaining that symmetry in all of the path lengths is also very crucial. So in my experiment here, it was actually quite challenging to get that, because these connections, shown here in these brown lines, these were cable connections, like cables made externally. So we had to find cables which were very precisely the same length. All of these other components also add some additional phase delay, so we have to make sure they were as similar as possible. And that was one of the limiting factors of this experiment, that we saw some loss. And remember, this one has a fourth port, which means that any imbalance means that power will excite the even mode and then get dissipated in this 50 ohm resistor out here. So that's sort of a loss in the system. It also gives a mechanism for additional noise to go into the system as well. So we sort of move to these kind of devices for doing differential excitation. But way back, one of the first experiments I was involved in during my PhD, I didn't design this, was the postdoc I was working with. This is another way of designing a transition which has a ground reference to something which doesn't have. Okay, so there's actually very little. It's a little tricky to see. Let me clear this. Focus on this part. This is a CPW transmission line. Okay, there is a thin center line, and there are two fat lines on this side. Okay, do you see that? On the right side, of course, is the coaxial connector which brings the thing, and you see a little solder which is used to connect. So this is a 3-conductor standard transmission line with plus V, 0 and 0, 2 grounds on either side. What has happened here is that you have basically cut short this line and slowly increased the width of this line and tapered it like this. This is also a way to go from a single-ended line to a differential line. Now, you might say, well, why is it differential? Because this line is the ground of the CPW. But do you see any vias here? There are no vias, which means here I'm actually allowing that ground potential to change. So it's grounded here, but it's not ground here because of the length. Remember, this was the thing I said, we cannot do this, because if you ground one conductor at one end, doesn't mean that it's grounded everywhere. So here we intentionally don't do that. So that by getting the center conductor and then the ground conductor similar dimensions, we now create a symmetric 2-line system. So you can think of this as either a coplanar strip line, because the gap between the two is very small, which is also the slot line which we had discussed, if you think about it. Or you can say it's a coupled strip line mode, because it's a coupled microstrip line, because this is a microstrip and that is a microstrip, but they can now have a differential voltage across each other. Okay. What we found was that this kind of transition worked well at low frequencies. At that time, we were doing the experiments, I think, at around 1.5 gigahertz. So it was okay. But at higher frequencies, this was not working very well, which is why we moved to those other type of ideas. So to finish with how we do this now, by the way, this is the same device we have been measuring. Is just a Josephson junction shunted with a capacitor. It's a nonlinear oscillator. It's sort of the only thing we measure. It's an amplifier, it's a qubit, it does everything. So we are constantly exciting, trying to find ways to use this. The latest way which we're using now in our designs is actually the simplest, in the sense that we don't really care about the terminal being ground here, because doesn't have any DC part. So what we actually do is we do a single-ended CPW, which looks like this. Okay, focus on the right side. That's a standard CPW. Okay, I could have made these grounds wider. So this is where the signal, so this is plus phi and 0. All we do is we bring the ground around and close it to the other side. Now I can put my device here. Okay. This works just fine. There are some caveats, and I just did, right? What did you not understand?
What do you say?
So I have this device and I would like to excite it with respect to ground like this, right? This is the voltage source. But that voltage source is coming in a coaxial geometry and coming onto a CPW line. So this is here a coplanar CPW with a center conductor and 2 ground planes. The problem is that if I can I connect it? Oops, sorry. I just realized that we have a even newer design which completely kills my explanation. but let me finish this. This is plus V and this is 0 and 0, right? And we use VRs or air bridges to keep the potential of the either side. I could put the device like this, but it sort of breaks the symmetry because I have not connected to this ground. Even though if these two things are nicely tied to each other in potential, it's okay, right? A more natural way of doing it is to just bring the ground around. I've just connected the 2 grounds, that's all. Because the 2 are anyway at the same potential, I've just brought them together. And now I have a nice symmetric way of exciting it. Okay. But as I realized that we now actually do it like this. And the reason for it is, if you needed a system like this one, where there is actually something else coming from the other side as well, closing the CPW on itself will prevent you from bringing something else from this side. So we now have a design where actually the ground goes all the way through. There are actually 2 transmission lines coming here. The device goes here like that. And that works is if you have done a good job of stitching the grounds of these 2 sides properly. So then it's not really an asymmetric termination because the 2 sides are anyway the same. And this we have now tested and it works quite well. So this is how we are going to be proceeding. So the idea here was to give you a flavor of how the same operation can be done in several different ways, each with its own pros and cons. And this is a very central thing in any microwave design. There are like 100 ways of doing it, but you have to find the one which is most robust for your application. And then, of course, in the context of the hybrid as a way to create differential signals as well. Okay, all right, it's 5:30. Any last quick questions before we go?
What exactly? I understand the paper, but then
Which part?
below that, the diagram.
This? Oh, this is nothing. This is
That's a row space.
where? This?
Yeah, this.
That's the other side of the ground, no?
When the line is tapering, so just
This?
continuation to that is a square line.
This part?
Yeah.
No, this part is where the CPW starts. Now there are 2 grounds to start with, and then you get rid of one of the ground. You just stop one of the ground. So this is kind of abrupt. The idea of this taper is that you want to do whatever you're doing, you want to do it gradually. So you're slow. Ideally speaking, you should take away the ground slowly far away so that the mode adapts to these 2 conductors. Okay. I'm not 100% sure if I'll have time to do that, but I did want to cover transitions as well. Transitions here means how do you go from one type of transmission line to another type of transmission line, because this happens all the time, right? In this figure itself, you are starting with a coax, then you have come to a CPW, and then you have become a CPS. Same way over here, you started with a coax, you went to a microstrip, then you went to a microstrip circuit, and then you finally ended with coupled microstrip lines. So these kind of transitions have to be done in a way that it's adiabatic. So there are no abrupt changes, because abrupt changes would mean that there'll be an impedance mismatch and you'll get reflections. So that's actually an important topic, but I'll see if I can cover this as well. So as I said, by this weekend, I will make the plan for all the remaining lectures and give you the timeline, and hopefully no cancellations from there. So 6th of?
Yeah.
Oh, you have this Mandar's conference. Yeah, it should be possible. Yeah. So if anybody is traveling or something, please send me an email so that I can work that around in the schedule.